All right. Today we will be discussing the recent 2024 February-March paper 4 that is worth 100 marks in exam. Before I start discussing the full paper, I'd just like to give a disclaimer that the question paper is not owned by GT Chem Channel and its owner, and the answers discussed in the question paper is not the marking scheme answers by the Cambridge Assessment International Education. All right. So the answer that I'll be discussing is just the opinion of the author and is used for discussion purposes only. All right. So just take it as a pinch of salt. Okay. Now, so let's go and dive into the question. So I received this question paper from a student and they want me to discuss the most recent paper. All right. So you can see here, it's 2024 February-March. All right. Without further ado, okay, we shall look at the first question over here. Potassium iodide is used as a reagent in both inorganic and organic chemistry. Potassium iodide forms an ionic lattice that is soluble in water. Define enthalpy change of solution. So it is defined as the enthalpy change when 1 mole of compound is dissolved in water to form an infinitely dilute solution. They do not have the standard word in front, so hence I do not need to answer under standard condition behind here. This part is not needed. But if they have the word standard up here, then yes, under standard condition part is needed. Number 2, potassium iodide has a high solubility in water, although its enthalpy change of solution is endothermic. Explain how this high solubility is possible. Now, if you obtain an enthalpy change of solubility endothermic, basically it means that you need to put heat, then only that 1 mole of solid is soluble in water. But if you get an exothermic number, then that means that 1 mole compound, when it dissolves in water, it will releases heat instead. All right. So this desolvation, also called the solubility of Ki, right, in water requires heat because it's endothermic. But then they say it has high solubility, even though it is endothermic. Okay. Now, 2 marks. I was wondering how to answer this question. Okay. Now, first, right, now I solved this by answering that the potassium iodide is able to form ion dipole interaction with water molecule. All right. So that's this to explain that they are able to be soluble in water because they can form ion dipole interaction. I personally think that this one perhaps will get 1 mark somehow, all right, because you can form interaction, which is the ion dipole interaction. And I did talk about when you form interaction or attraction, it is releasing energy. All right, I did realize it is a releasing energy, even though the net total is still endothermy. Okay, and because solution, all right, is defined as minus Le plus hydration, right? Okay, so if you want a total endothermic here, that means lattice energy is always negative for information. Hydration is always negative. So what it means that lattice energy is actually more exothermic. So when you minus a minus lattice energy and you plus a negative hydration number, then net total will still be endothermic. All right. So I did say that it is still able to overcome the lattice energy between the K plus and I minus. All right, even though the lattice energy magnitude number will be quite big, all right, but still able to overcome because they have large ionic radii between the small positive and negative one charge. So they are actually having a low charge density for K plus and I minus. All right. So not too sure whether is this what they want. And suddenly my idea came. Maybe the second answer, the second point, maybe perhaps the activation energy is low for the enthalpy change of solubility of Ki. Maybe these two are the 2 marks. Maybe. This is just my personal opinion. Okay. Now, part B. So part B, they gave us some data on the halide and their potassium salts. So they gave the hydration of the halide ion and they gave the lattice energy of the potassium halide. Okay. Explain the trend in enthalpy change of hydration of the halide. So you want to look at the middle column to explain the hydration. So I just say that the enthalpy change of hydration is less exothermic. Please don't use increase, decrease. Increase, decrease in which direction? Okay. We have to be more specific. Is becoming less exothermic. As you can see the number here, less exothermic. All right. Why? It's because the halide ion size increases with the same -1 charge. Hence, the charge density decreases. Okay, I underline the keyword. Now, therefore, when your charge density decreases, the ion-dipole interaction form, all right, will be weaker with water molecule. So when you form weaker interaction, I did state my last sentence, a weaker interaction will result to a less exothermic enthalpy change of hydration. This is just my answer. Okay, now, second question. The enthalpy change of solution of the potassium halide are almost constant. That means after you put into the formula, using this formula, solution equals to minus Le plus hydration. If you put in the number one by one row by one row for the chloride, bromide, and iodide, the enthalpy change of solution are almost constant. That means it does not change significantly. All right. So use the hydration and lattice energy data in the table 1.1 to suggest why. I look at the table and I went and find the change between the chloride and the bromide. So let's look at the data here. So when I look at this, here has a change of 29. Here has a change from 31. Okay. The change is quite similar. All right. And then from bromide to iodide, the change is 42 and the change is 41. So the change in the chloride to another ion called bromide, right, it's approximately around 30. All right. So perhaps that's the reason why the enthalpy change of solution is constant. All right. When you put into the formula, when you recalculate everything, it's going to be approximately around. So let's just take a calculator. You can just take solution equals to minus Le, which is this. Okay, minus Le plus hydration, which is okay. So the enthalpy change of the halide ion is around 337, not knowing what is potassium now. All right, so you can go and calculate. But to me, I just look at the change in the halide ions. All right, so if you look at my answer, I just say because the hydration and lattice energy both become less exothermic with a similar magnitude. From chloride to bromide, there has a change about 30. Bromide to iodide, there's a change of 41. Okay. Next, enthalpy change of solution of Ki is positive 21. Use this information and the data to calculate the enthalpy change of hydration of potassium ion. So I take out the formula, solution equals to minus Le plus hydration. So solution is positive 21. Lattice energy, you go to the table, is minus 629. Hydration of iodide is minus 293. You want to find hydration for potassium, right? So therefore, I calculated minus 315. The working is there. Okay, now next. So solid PbI2, which is lead iodide, forms when Ki is mixed with Pb2+. So PbI2 is a yellow PPT here. Okay. So the solubility product Ksp of PbI2 given is 7.1 times 10 to the power -9 at 25 degrees Celsius. Calculate the solubility in mole per dm cube. Please be reminded that you only can use mole per dm cube for Ksp. Please do not use gram per dm cube. If the question gives you gram per dm cube, you need to convert gram per dm cube to mole per dm cube. Must. Okay, because you cannot have how much gram per dm cube on the left hand side here to give how much gram per dm cube and 2 times gram per dm cube. So you will actually come up with 3x on the right hand side. All right, and then you start violating the conservation of mass law. For example, if you have 10 gram of lead iodide on the left, if this is x, that means this is x and this is 2x. So if you use gram per dm cube, you're trying to say that 10 gram per dm cube on the left will give a total of 30 gram per dm cube on the right hand side, which will violate the conservation of mass. So that's why you cannot use gram per dm cube for Ksp. All right. So first, I always say, write the equation out and fill in your x, x, and 2x. Then you write your expression. Okay. So expression is Ksp given here. So you put in the Ksp value here. All right. And you can find what is x. Now you must know what is x. X is solubility. X is also the concentration of lead 2+. 2x is the concentration of iodide ions. So the question wanted the solubility of PbI2, which means this particular lead. So it happens to be x. So therefore, the answer is 1.21 times 10 to the power -3. Next question. Ionic radius of lead 2 plus ion is 0.12 compared to 0.133. So you can see that lead is smaller than potassium. All right. And suggest how the lattice energy of lead iodide differs from the lattice energy of Ki. This is quite straightforward. Lead has a higher charge, which is +2, and a smaller ionic radii. So I did say that charge, okay, the charge density for Pb2 plus will be higher, okay, than for K plus of a bigger charge and a bigger ionic radii. Oh, sorry, K plus of a smaller charge, smaller charge. K plus is smaller charge. Let me change this. And a bigger ionic radii. All right. So when you have a higher charge density, what does it mean? It means that the ionic bond or the electrostatic attraction between the Pb2 plus and I minus will be stronger. So what does it mean to have a stronger electrostatic attraction? Or what does it mean to have a stronger ionic bond? It means that more energy will be released. Okay. Hence, the lattice energy is more negative. All right. Very detailed explanation. Now, next. All right, so they gave us a data of the entropy changes, okay, and calculate the standard entropy change for the reaction. So when you want to calculate the standard entropy change, delta S, summation of product minus the summation of reactant. So if I were to zoom out, okay, I calculated to an answer of minus 514.4. If my final answer is not correct, that means basically the working is still correct lah, because I just did it one time. I didn't go and check second round. Okay, but the working is correct. You have to take 2 times of potassium carbonate. So 2 times 155.5 plus 2 times of iodine, which is 2 times of 116.1. You sum it up and you minus the total summation of the reactant. Okay. Now next, use your answer in C1 to show that the reaction 1 is spontaneous at 298. So spontaneity or feasibility, you need to bring up Gibbs free energy, which is delta G. So delta G equals to minus Ts plus H. So 298. All right. Now, sometimes the question don't tell you at 298. All right. But the fact that you saw is theta, right? This is theta, right? Okay. This is also theta, right? And obviously, when you calculate, you only can calculate what is delta G theta. So hence, even if the question never say 298, right, you should also take it as 298 because standard condition means 298 lah. All right. But because the question very nice, they tell us at 298, then you thank you very much. All right. So you put 298. Now remember, don't make this careless mistake. Entropy is joule. You need to convert to kilojoule. So 514.4 divided by 1000, and then you plus delta H. So that delta G, everything will be in kilojoule per mole. So when delta G is negative, it is spontaneous at 298, only at the particular temperature. All right, next part. Group 1 carbonate are much more thermally stable than group 2. State and explain the trend in the thermal stability of group 2 carbonate. Okay, so state and explain. Can I just add one sentence behind? All right, so I will just say that I did say the last sentence, group 1 carbonates are more thermally stable than group 2. Basically, I'm just re-quoting the question, right? But that is my conclusion now. Okay, so the trend in thermal stability of group 2 carbonates. Okay. All right. So basically, everybody, just ignore this. Okay, just ignore this, Just ignore this. You want to explain a group 2, I thought you want me to explain group 1. Okay, never mind. I can just write the answer up. Now, so group 2, thermal stability, all right, increases down the group. Okay, that's one point. Okay, why? Because the cationic radii increases down group 2 with the same positive 2 charge. Hence, charge density of group 2 ion decreases. All right. Polarization on the carbonate decreases. All right. So what does polarization on carbonate decreases? Well, it just means that there is less weakening of the CO bond in carbonate. Going down, group 2. That's it. Okay, so feel free to pause the video, or if you want to like copy down the answers, all right? And I will just progress to the next question here. Okay, donkey. The student electrolyzes a solution of potassium iodide aqueous for 8 minutes. Aqueous means there is competition of cation and competition for anion for the respective electron. So the half equation for the reaction at the anode is given. Remember, anion move to the anode. So I minus is an anion, it moves to the anode. Anode is forever oxidation. All right, true enough, you can see the equation is written in oxidation format. Okay, so they want you to write the half equation that occurs at the cathode. So cathode is for cation because it rhymes. Okay, so for cation, you have K plus. So the careless mistake is student will go for K plus. Okay, but the correct answer is H plus because you're using aqueous. So aqueous has H plus, and you should know by now that H plus is the electropotential value 0.00. Okay, and for potassium is negative 2.92. It's a very big negative number. So for the discharge of cation, we will pick the more positive E value, which is 0.001. As in 0.00, the one that will be discharged, all right? Because 0.00 is more positive. So you will liberate hydrogen gas instead, so not potassium metal. After the electrolysis of the iodine, after the electrolysis, the iodine produced requires 21.35 of 0.1 sodium thiosulfate. Okay, so normally iodine and thiosulfate, they react together. So calculate the average current used in 8 minutes. So first, I calculate the number of moles of the sodium thiosulfate. So the moles of sodium thiosulfate here is 2.135. According to stoichiometry of equation, you calculate back the iodine, which is half of the sodium thiosulfate. So this is the number of moles of iodine liberated or deposited in your 8 minutes electrolysis experiment. Now, according to theory, take out theory, you calculated experiment already. Now bring out your theory. According to theory, right, we realized that 2 Faraday, because 2 electron is required, 2 Faraday is required to deposit 1 mole of iodine, according to the half equation given. So 2 Faraday means 2 times 96500, which is 193,000 quantity of charge, then only can form 1 mole of iodine. You need to provide 193,000 quantity of charge, then only you can get 1 mole of iodine. So now your experiment only gave 1.06. So 1.06 means you only had 206 quantity of charge in your experiment. So your experiment only passed 206 total quantity of charge, not 193,000, because your mole is so little, 1.0675. So once you know the quantity of charge, then Q equals to IT. So time must be in seconds. So they give me minutes. You need to times 60. Therefore, the current is 0.4293 significant figures minimum. All right, so that is what I have calculated. Okay, now let's move to the next question. So Ki is used as a source of iodide ions in organic synthesis. So one example of this is shown in the synthetic route in figure 1.1. All right, so let me just zoom up the whole thing. Okay, zoom on. Now, can see the whole page. Now, identify the reagents. I underline reagents. So they never ask for condition, right? So I omitted out all the condition. So step 1, you can see that is nitration because you added nitro group. All right, so what do you need? Concentrated HNO3, concentrated H2SO4. So you can look at my answer down there. All right. Now, the condition is 55 degrees Celsius. But because they did not require condition, so hence I did not write the 55 degrees Celsius here. Step 2. Step 2, as you can see, it's a reduction of the nitro to the amine. All right, so it's a nitrobenzene to a phenylamine. Okay, so what do you need? You need the reagent, tin, concentrated HCl, followed by dilute NaOH. Followed by dilute NaOH, normally they don't award mark. It's always in bracket one. Okay, but I will still do my part to write followed by dilute NaOH, because if you don't follow by dilute NaOH, right, normally this part will come out as NH3 plus because it's concentrated HCl. So there's a lot of proton. The proton will be protonated on the phenylamine. So if you want to take out that proton to give a neutral phenylamine, then you have to put followed by dilute NaOH. That is theory. Okay, but I know marking scheme normally they don't award the bracket part. Now, what is the condition which is not needed here for this particular question? You need to heat under reflux. Okay, but I've been looking at the recent 2023 marking scheme. Normally they put here hot tin. All right, it basically means it's heated up. All right, so if you look at very maybe like a little bit earlier, let's say maybe 2021 2020 marking scheme, they will just say the whole thing heat under reflux. Also can you want, you can put hot tin, you want, you can put heat under reflux, also can. Okay, but I did not put the condition here because it's not required. Now, step 3 occurs in 2 stages, which is the diazotization. So diazotization occurs in 2 stages. Number 1, they tell you NaNO2 and HCl undergo acid base to produce HNO2. So we call this in situ production of the nitric acid. You have to do it freshly on the spot. Why? Because HNO2 will quickly be oxidized to HNO3. If you make it yesterday, by today you want to use it after one night, all your HNO2 will be converted to HNO3. That's not what you want, right? If you want HNO2, then you freshly produce it then there. That's the step 1. So construct an equation. So therefore, you just swap the ion acid base. We can see that the HCl donated a proton. Okay. Therefore, it becomes HNO2 and NaCl. Stage 2 is the diazotization. Okay, now diazotization needs to be done under acidic condition. So I predict a lot of Cullen's mistake here. All right, otherwise you can't balance the positive charge. Every equation needs to be balanced in terms of atom and charge. So diazotization is a positive compound. So who was responsible for the positive? Is because at the reactant there, you have an acidic condition, which is H+. So the H+ is provided by HCl. So for those who want to write HCl here, then that means you have a chloride up here. So because chloride is a spectator, so I'll just remove the chloride and remove the chloride, just so you know. Okay, and you should know it must be done below 10 degrees Celsius or maybe 5 degrees Celsius. Otherwise, your benzene diazonium ion will decompose to nitrogen and phenol. So your stage 2 must be done below 10 in acidic condition. All right. Then after that, the coupling reaction subsequently, normally they'll couple with phenol, or maybe naphthanol or naphthol. That one requires NaOH. So the azotization is acidic condition, coupling is NaOH, alkaline condition, also below 10 or 5 degrees Celsius. Now the next part, the iodide from the potassium iodide reacts with D in step 4. Okay. The mechanism is shown in figure 1.1. Suggest the name for this mechanism. Now let's look at step 4 here. They wanted the mechanism here. All right. So what we can see here is this is a nucleophile. Nucleophile is a compound or a species that can donate a lone pair electron. So nucleophile is the first word. Second, if you look from here to there, it's a substitution reaction. Hence, I answered nucleophilic substitution. All right. But I know that in our syllabus, when we learn about benzene, the mechanism is electrophilic substitution. But this is an application question. I see that iodide has a lone pair. It's not a positive charge. So it's not positive charge like electrophile, nor it is a lone pair deficient species. Iodide is not a lone pair deficient species. So it's not going to be an electrophile here, 100%. So this is a very clear-cut nucleophile case. Okay, so for me, the answer is nucleophilic substitution. All right, let's go to question number 2. Now, water is an amphoteric compound that also acts as a good solvent for polar and ionic compounds. So equation 1 shows water acting as a Bronsted-Lowry acid. water as Bronsted-Lowry acid. Okay, now first what I do is I go and find the correct pairs, all right, one from the left and one from the right. So you can see I pair up H2O, all right, because they say H2O is an acid. Acid means you need to donate proton, then you will form hydroxide. So identify the two conjugate acid-base pair in the equation 1. So since the first one, they said acid is H2O, that means your conjugate base on the right-hand side is hydroxide. Now, then what is the acid 2 then? The acid 2 means acid is still donating of proton compound. So your acid 2 has to be the right-hand side, HNO2, because if you read the equation backwards, HNO2 moved to the left, he donated a proton. Okay, so the acid 2 is HNO2 and your conjugate base is NO2 minus. Water can also behave as the Bronsted-Lowry acid when it dissolves in methylamine. Explain the ability of methylamine to act as a base. So a base is to use its lone pair electron to accept a proton. Accepting a proton means base, but the ability of the phenyl or the methylamine is to use its lone pair electrons on nitrogen. Write an equation to show water acting as a base. So this time, water want to act as a base. So water accepted a proton to become hydronium ion, H3O+, whereas your carboxylic acid donated a proton. Okay, now next. Any product of water, Kw, measures the extent to which water dissociate. So given the dissociation of water equation here, now, and then they give us a graph here to show how temperature varies with Kw or how Kw varies with temperature. Write an expression for your Kw, straightforward. Kw equals to H plus times OH minus 1 for 1. Use information from figure 2.1 to deduce whether dissociation is exo or endo. Now, so the answer is this. Kw increases when temperature increases. Now, this is not the answer yet because you're just literally repeating what the graph is saying. I mean, yeah. So when temperature increases, Kw also increases. All right, this one got no mark. Okay. Now, the mark is the dissociation of water is endothermic. This is the one. Why? Because an increase in temperature will favor the right-hand side for an endothermic reaction. Therefore, your product will have a higher concentration. So what is your product? Your product is the multiplication of the H plus and the OH minus. So when this one goes up, your Kw also goes up. All right. Now, third question. Okay. Now, I'm not so sure how many people can answer this question. I think this is a nice question. Aqueous solution has pH 7 at 30. Use information from figure 2.1 to explain why this solution can be considered to be alkaline. Now, first, I went and looked at the graph. What is the Kw at 30 degrees Celsius? Now, your 1 times 10 to the power of negative 14 is only valid at 25 degrees Celsius. So if you look at your 25 degrees Celsius here, you will realize that your Kw is your so-called Ln 1 times 10 to the power negative 14. That is at 25 degrees Celsius. But if you look at temperature, temperature affects all sorts of K. All right, Ka, Kb, Kw, Kc, Kp, whatever K you want, temperature affects all K. So when you look at 30 degrees Celsius, right, and I found out that the Kw at 30 degrees Celsius is 1.5. All right. Now, so the water, ionic product of water will change according to temperature. So now they want 30 degrees Celsius. So you look at my answer. At 30 degrees Celsius, look at the cursor. The Kw is found to be 1.5 times 10 to the power 14. Now, what is Kw? Kw is H plus times OH minus. So because the H plus and OH minus is a 1-to-1 ratio, so therefore I can just square. All right. Square 2. Okay, square. So therefore, what is H plus? All right, concentration at 30 degrees Celsius. So I just square root 1.5. Therefore, the H plus concentration is 1.22. So if I negative log 1.22, that means the pH of water is 6.9 at 30 degrees Celsius. What it means is this. pH 6.9 is neutral at 30 degrees Celsius as it has equal amount of H plus and OH minus. This calculation, you are making it where 1 H plus will give 1 OH minus, or 1 H plus is existing with 1 OH minus, because when you dissociate one water molecule, every 1 H plus will be balanced out by 1 OH minus. That's called neutral. So when I calculate the pH of the 30 degrees Celsius, apparently 6.9 is considered neutral. So if you want to drink water, please drink 6.9 at 30 degrees Celsius, provided your throat can take 30 degrees Celsius water lah. Okay, so 6.9 means neutral at 30 degrees Celsius. 25 degrees Celsius, neutral means 7. 30 degrees Celsius, 6.9 means 7. Understand? All right. Now, therefore, why 7 is considered as alkaline is because 7 is higher than 6.9. So anything higher than 6.9 is considered alkaline. Understand? Okay, so at 30 degrees Celsius, the neutral point is 6.9. Anything above 6.9 is considered as alkaline at 30 degrees Celsius. All right, now let's move. There are 3 physical states of H2O, all right, and they give you the standard entropy data. Explain the difference in the entropy values of the solid version and the liquid version. So I said liquid has moving particles and is more random and more disordered compared to solid. Hence, the entropy change of liquid is more positive than solid. It's more positive, not higher. Okay, not endothermic. Endothermic, exothermic is only for delta H. The rest is called more positive, more negative. Okay. Explain why the increase in the entropy change is much greater when your H2O boils when it melts. So liquid boils to gas will form more random moving particle because gas will move more random as compared to liquid. All right. And gas is more disordered. So I say that it is forming more random moving particles and more disorderedness compared to solid when it melts to liquid. So liquid will have a low disorderedness. So that's the reason why the change in boiling is greater than the change in melting. Both will have a positive change. It's just that boiling will have a greater change. Okay. The energy changes for the melting is shown. Now, melting means equilibrium between solid and liquid. Okay, so use this data to show that the melting point of H2O is 0 degrees Celsius. So first, I need to find the entropy change. So entropy change is product minus reactant. So product means H2O liquid. You go to the table. Okay, I zoom out a bit so you can see here. So can you see H2O liquid is 70.1? Okay, product minus reactant. Reactant is 48. Okay. So the entropy change is 22.1 joule per mole per Kelvin. Then you put into the formula. Delta G equals to minus Ts plus H. Okay. So at equilibrium 0. Okay. Equilibrium is 0. Now, anyhow, if you don't know also, the question already told you is 0. Okay. Now, delta G is 0. Then you put the number in. Again, entropy, please convert to kilojoule per mole. All right. And then delta H given, you should be able to calculate out that the temperature is in 272.9 in Kelvin terms. But they wanted degrees Celsius. So Kelvin, all right, to convert back to degrees Celsius, you need to minus 273. So proven 0 degrees Celsius for melting point. All right. Next. Metal air batteries are electrochemical cells that generate electrical energy from the reaction of metal anode with air. Standard potential for the zinc air battery are shown. Calculate the standard cell potential. You wanted zinc air. Okay, now my usual practice is to align from most positive to least positive. But because there's only 2 equations here, or 2 half cell, I think I still can do it. But if we give a lot, right, many E value, then yes, I will spend a little bit time in the exam to rearrange from most positive to least positive. So because you wanted zinc and you wanted oxygen, right? So hence, I circle zinc, I circle oxygen. Okay, so what we know that the more positive will undergo reduction and the less positive will undergo oxidation. So the formula for E cell is more positive minus less positive. So E cell value is 1.62, which is correct, oxygen and zinc. All right, so it's called zinc air battery cell. So the zinc air battery usually operates at pH 11 at 298. The overall cell potential is dependent on the hydroxide concentration. Nernst equation show how the electrode potential at the cathode changes with hydroxide because hydroxide will be used. All right. So when the hydroxide concentration decreases over time, then yes, your electrode potential will also changes over time. That is correct. Okay. So calculate the electrode potential at pH 11 because we need to run it at an alkaline condition. Now, so over here, they already gave us the formula for the Nernst equation in their version. But of course, if they never give it to you, right, you're supposed to use your own Nernst equation to solve the question, which is still doable. Okay, so for them, they're kind enough to help us for the Nernst equation, but you shouldn't expect it. All right. Calculate the electrode potential. Come. So first, given pH is 11, I find what is the concentration of H plus. So H plus is 10 to the power of negative 11. All right, that's the concentration. So I need to find what's the concentration of hydroxide. So hydroxide is Kw divided by H plus. So Kw is 1 times 10 to the power negative 14 at 298. So therefore, I can calculate the hydroxide concentration at 298 is 1 times 10 to the power negative 3. Then I put it into the Nernst equation. Now, if you look at the equation up here, 2 electron is being involved for the hydroxide. Okay. Can I just cathode now? Let me just re-look again. Whether do I still want it a 2? Yes, 2. 2. Because no matter which equation you pick, right, it's still 2. You understand? Which equation you look is still 2. All right. So therefore, the Z is called 2. And then I put my hydroxide concentration and I square according to the formula given. So therefore, the E value calculated is 0.223. Yeah. Okay, let's continue. Question 3. Iron is a transition metal in group 8 of the periodic table. Explain why iron has variable oxidation state. Okay, so there are 4 chemical properties of transition element. I hope you know by now. All right, and number 1 is they can have variable oxidation states. All right, and why? So the answer is because the 4s and the 3D energy levels are similar. Hence, after removing the 4s2, you can continue to remove more electrons from the 3D. So if you only can remove from 4s2, right, the maximum you can go is called 2 plus after donating 2. But you can have 3 plus, 4 plus, and 5 plus in transition element. It means that you can donate the 3rd, the 4th, the 5th electrons. And where did the 3rd, 4th, 5th electron came from? It came from the very near 3D energy level orbital. All right, so that means the 4s and 3D energy levels are very similar. So hence enabling more than 2 electrons from the 4s to remove from the more than 2. Remove from the 3D. Okay, 4s and 3D onwards. So complete the shorthand electronic configuration. So for some students who are not familiar, please familiarize argon. Argon is 1s2, 2s2, 2p6, 3s2, and 3p6. All right, it's 18 shorthand. Okay. Now then, if you look at your periodic table, iron, metal, all right, the neutral form is 4s2, 3d6. 3 plus means you need to remove 3 electrons. So you remove from the 4s2 and 1 from the 3d. So therefore, it's 3d5. An aqueous solution of the iron 3 nitrate contains the complex iron 3, which is in the hexa-aqua form. All right, so this is complex ion. When solutions of potassium thiocyanate and hexa-aqua iron 3 ions are mixed, when these two are mixed, a color change is observed. The red complex is formed. Define complex. Okay, so it can be complex molecule, it can be complex ion. All right, so complex is when one or more ligand is attached to a central metallic atom or a central metallic ion. Maybe I would like to continue a bit more via coordinate bonding. Okay, via coordinate bond. State the coordination number of the ion in this complex, 6, because there's 6 coordinate bond here. So the coordination number is defined as the number of coordinate bond formed. Okay, so there are total 6. Now, H2O bond angle in water is 104.5. So if you still can recall, H2O, 2 lone pair, 2 bond pair, 104.5. Lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. But when you use one of the lone pair and you form directly to your Fe ion, all right? So therefore, you have how many bond pair now? 3. You have 1 bond pair here, okay? 1 here and 1 here, okay? So you have 3 bond pairs and 1 lone pair. So maybe the angle 3 bond pair is, yeah, let me think. 3 bond pair and 1 lone pair. Let me just think. As you know, okay, let me solve. Oh, sorry, 107. Sorry, I changed my answer. 107. When you have 4 bond pair and 0 lone pair, this is tetrahedral. Okay, shape. So the angle is 109.5. Now you have 3 bond pair because 2 is with the hydrogen, 1 is the coordinate bond to the ion, and you still got 1 more lone pair, right? Then this is trigonal pyramidal of 107, like your ammonia case. Okay, so I changed my answer, 107. 107, okay, as the lone pair electrons on oxygen was used to form a coordinate bond with the central Fe3 plus ion. Hence, there are 3 covalent bonds and 1 lone pair and 1 lone pair around the oxygen atom, giving a, trigonal pyramidal shape. I know they never ask for shape, but I'll normally angle and shape comes together, but I suppose your 107 will get the mark. Okay, maybe they will require you to add on to explain by using 3 bond pair and 1 lone pair. All right, so you can see the highlighter, the 3 bond pair and 1 lone pair will give 107, just like ammonium. Next, explain why ion complexes are colored. Very expected question. Okay, so normally the first one we need to see is the d orbital splits to 2 different energy level. Okay, and I just add on a little bit to say that they are non-degenerate d orbitals after they split, and they have an energy gap in between the 2 d orbitals. Now, then I did say that iron has an incompletely filled electrons in its d orbital, which is definition of transition element. A wavelength of visible light is absorbed. Okay, normally is this. All right, to promote an electron from a lower d orbital to a higher d orbital. Normally, the last bullet point would be the color observed is complementary to the color of the wavelength absorbed. So if you were to absorb blue, that means the complementary color will be orange. So the transition complex will be orange color. Okay, so normally this kind of question, 4 bullet point, 3 marks, 3 bullet point, 2 marks, 2 bullet point, 1 mark. Okay, now next. Aqueous solution of the 2 complexes are different. Why these complexes are different color? First, I say that the ligand attached are different. Okay, hence the energy gap will be different. I believe energy gap different is one of the key mark. Okay, so therefore, when your energy gap is different wavelength of light will be absorbed. Okay, so maybe one absorb red, one absorb blue. Okay, so different energy gap caused to different visible light wavelength will be absorbed to promote an electron from a lower to a higher d orbital. Hence, the color observed that is complementary will also be different. Okay. Now, let's look at part C. Table 3.1 gives the value for stability constant of different complex. So I hope you know what is definition of K-step. Okay, go and revise your K-step definition. So given these two, now write an equation for this reaction where the first one is formed when H3PO4 reacts with the hexa aqua ion 3 plus ions. Okay, so you can check the equation. So your H3PO4, okay, will plug one proton, okay, will donate one proton to the aqua, okay. Yep, it will donate one proton. So because H3PO4 now become H2PO4, so they donate one proton to become H3O plus, okay. Now, write an expression for K step and give its units. So, to form this complex, right, you must always start from the status quo called the hexa aqua. All right. So no equation is given. If you do a lot of past year, then you realize nowadays when they ask you to write a K step expression, they normally don't give you the equation. If they give it to you, then nice. But normally they don't give it to you. So K step is defined as the formation of this particular complex. So when you want to form this complex, you must always form from the status quo called hexa aqua version. All right, 3 plus. Okay, 3 plus. So FeH2O6 3 plus times thiocyanate. Thiocyanate is negative. I hope you know by now. Okay, now then over here, yes, I know H2O will be removed, but H2O must always be omitted out from K step. All right, so unit is mole negative 1 dm3. Use the stability constant in table 3.1 to calculate the value of the equilibrium constant Kc for the following equilibrium. Now, so K step is the formation of the complex. So basically, your arrow had to form up. You are forming this particular complex and you are forming this particular complex. Though this is called K step. You form. So the arrow must point to that particular complex. How do you form? Well, basically, you form from the status quo, the hexa aqua copper 2 plus 3 plus ion plus the other ligands. Okay, so the hash cycle is not needed, so I never completed the third leg down there. Okay, but the arrow must be pointing to that too. So direct equals to indirect. So therefore, you need to take a minus 5.9 times 10 to the power of 1, and you plus a 1.3 times 10 to the power of 2. Okay, so my answer come out is 71. Okay, direct equals to indirect. That's according to Hess's law. Okay. Question number 4. Ruthenium and osmium are transition metal below iron in group 8 of the periodic table. Two different complex ion X and Y can be formed when anhydrous ruthenium chloride reacts with water. So X and Y have octahedral geometry. That means they have 6 coordinate bonding. Aqueous sample of X and Y react separately with excess silver nitrate. So silver nitrate job is to pick up the chloride ions, not chloride ligand, chloride ions, the anion version. Okay, so different amount of silver chloride are precipitated. So 1 mole of complex X produces 2 mole of silver chloride. So silver plus will pick up chloride anion. So if you got 2 AgCl, that means you got 2 Cl minus as anion. Understand? So you have 3 to start off. If 2 is outside as an ion, that means 1 is inside as a ligand. So if you look at the formula for my compound X, can you see this is called 2 chloride as the anion? Because when silver comes in, 2 silver and 2 chloride will give 2 silver chloride precipitate. Okay, now this complex is positive 2. Why? Because positive 3 with 1 negative will give positive 2. This positive 2 will be balanced by 2 chloride. Okay, now they did not tell us that iron is 3 plus, but the fact that you use 3 chloride, right? Then you know that your iron, how come I use iron? Sorry, not iron. Please change iron to Ru. Okay, Ru. Ru. Please change this to Ru. Then okay. Okay, so they behave like iron, the first statement really. So iron normally +2 +3. Okay, yes, we do not know what is the oxidation number of the ruthenium. We don't know. Okay, but based on the 3 chloride used here, all right, you know that ruthenium is +3, because here got 3 chloride, Okay, Yep. Now then, if you look at complex Y produces 1 mole of silver chloride. 1 mole of silver chloride means 1 chloride as anion version. So you can see this is 1 chloride in anion version. That means out of 3, 1 is anion, the other 2 must be inside here as ligand. Okay, yeah. So in total, your complex must always have 6. Okay, because they say octahedral. So can you see here, there's 5 water molecule and 1 chlorine. So 5 plus 1 is 6 octahedral shape. Since here got 2 chlorine as ligand, that means the remaining 4 must be water. So there are still total 6 ligand in the octahedral complex. Okay, so the formula is given as the blue color pen, but please change Fe to Ru. Now, both complexes react with excess bipyridine, BIPY, to form a mixture of 2 stereoisomers. Okay, so they did say that bipyridine is a bidentate ligand, correct? Because I can see you got 2 lone pair of electrons that can be donated per ligand. So draw 3-dimensional diagram. So 3-dimensional diagram, please remember to draw your wedge ring, which is a triangle, and the dotted line backstage. Okay, so when you have 3 bidentate, you will show optical isomerism. So you can see I draw it in mirror effect, optical isomers. Yeah, but please remember to not clamp your bidentate opposite. Means you cannot clamp from top to bottom. This clamping cannot, because this is 180. Okay, bidentate cannot go across. Bidentate is 90 the most. So you can see this is 90. This is 90 between the 2 nitrogen, and this is also 90 between the 2 nitrogen. Okay, bidentate can only clamp at 90 degrees apart. So figure 4.1 shows another ruthenium complex. Okay, this complex contains the neutral ligand. Now, when I look at this, right, this part is neutral. Ammonia, NH3, is neutral. Ammonia is neutral. Everything here is neutral. Okay, so the only one that is responsible for the 5 positive charge is your ruthenium, because all the ligands here are neutral. Suggest how pyrazine is able to bond to 2 separate ruthenium ion. There is 2 transition metal ion here. Okay, so how are they able to bond to 2 transition ion, which is your ruthenium ion? Well, I said because it uses its 2 lone pair of electrons on 2 different ends of nitrogen to form 2 separate coordinate bonding with the 2 ruthenium ion. Okay, yeah. Now, next, pyrazine is an aromatic compound. The bonding and structure of pyrazine is similar to that of benzene. Describe and explain the shape of pyrazine. Now, drawing is not necessary, but since they gave space, so I just draw for the sake of the discussion. Okay, so in your answer, include hybridization of the nitrogen and carbon. So I said the carbon and nitrogen are all sp2 hybridized. The shape is trigonal, planar, and 122 angle. I know they never ask for shape, but if you do enough past year, you normally know that they would like to see the angle and the shape. All right, no harm including it in. So how the orbital overlaps form pi bond between the atom in the ring. Okay, so they only wanted pi bond, right? Okay, I added too much, so I also put sigma bond. So maybe this is not needed. So we just look at the last one. Pi bond is the sideways overlapping of the p orbital of carbon and nitrogen, carbon and carbon. So if you look at the structure here, right, this is how a benzene look like. It's just that we changed this to become nitrogen and nitrogen. All right, originally is carbon in a benzene. So we just change it to nitrogen. So you can see that there is a sideways overlapping. Look over here. There's a sideways overlapping from the nitrogen and the carbon, sideways overlapping of the 2p orbital. We also have sideways overlapping of the 2 carbon, also got. All right, so that's why I said that pi bond is a sideways overlapping of the p orbitals of carbon and nitrogen, carbon and carbon. Okay. Predict the number of peaks seen in the carbon-13 NMR spectrum of pyrazine. So I draw the pyrazine here. Now, there's only 1 peak. Why? Because as you can see, that pyrazine molecule is perfectly symmetrical. All right. So therefore, if you cut it this way, you can see the mirror effect is like this. It's symmetrical left-right. So it means that this carbon is the same as this carbon. But if you were to cut this way, then you will realize the symmetry point is up-down. Okay, so it means that this carbon is the same as this carbon. So therefore, there's only one type of carbon on pyrazine molecule. Hence, you're going to only have one signal in carbon 13. Okay, so I just said one peak. As the molecule is symmetrical, it has only one type of carbon. Yeah. Deduce the overall charge of ruthenium. Okay, so deduce the possible oxidation state of the 2 ruthenium. The whole complex is +5. You can see here. Whole complex is +5. And there's 2 ruthenium. What is the possible oxidation state of the ruthenium? So 1, 2, and 1, 3. All right. Which one is 3? Which one is 2? Don't need to know. We don't know. All right. Yeah. But because it behaves like iron is +2 and +3. So therefore, 1 is 1, 1 is 2, 1 is 3. The total charge is 5. So osmium tetroxide, OSO4, reacts with alkene in a similar manner to co-dilute acidified manganate. Co-dilute acidified manganate means you need to form a diol, okay, across the double bond. So you need to form a diol. Okay, so they say it behaves similar way to your alkene. So what happened here is, since you gave me the information, right? So that means this one, you need to put a diol across the double bond. So I put the double bond here. I put the OH, the diol here. And I actually did count it. All right. If you count the whole carbon, hydrogen, and oxygen, it is correct to C6H12O2. Number 1, suggest a reagent for step 1. So for step 1, you can see you're converting carboxylic acid to acyl chloride. I suggest PCl5. Other optional answer, PCl3 plus heat. Also can accept SOCl2. No HCl. Cannot. Okay, HCl cannot be used to convert carboxylic acid to acyl chloride. Draw the structure of exactly 1 repeat unit of condensation polymer G. So let me zoom out a bit. Okay, so this is the answer for the 1 repeating unit. The ester linkage must shown fully displayed. So I did show the bond C double bond O, C single bond O ester. All right. So you need to draw your diol out here first. Then only you go and merge it with the diacyl chloride. Okay. You may pause the video. All right. To go and write down your answer. Now, question number 5. Compound Q. Boom. The whole page. Okay. Compound Q can be synthesized from chlorobenzene in 7 steps using the route shown in figure 5.1. Okay. Now, write an equation for the formation of the electrophile for step 1. So let's look at step 1. They want us to write the formation of the electrophile. So this is very straightforward. Okay. So therefore, the answer, please check. AlCl3 plus CH3Cl to give AlCl4 negative, and your electrophile, which is the methyl carbocation CH3 plus. So step 1 is actually the alkylation. All right. Let's do a little bit quick recap. So Friedelscroft alkylation need heat. Any Friedelscroft alkylation, Friedelscroft acylation, please write heat. Okay. Now, so chlorine is an electron withdrawing group. Now, electron withdrawing group will normally direct incoming electrophile to the C2. All right, this is C2 position and C4 position. Okay, chlorine is an exception. Chlorine is an electron withdrawing group that will direct to C2 and C4, because normally if you're an electron withdrawing group, you will direct to C3 and C5. But this particular chlorine electron withdrawing group is an exception case. Instead of C3, C5, it will direct to C2, C4. Okay. Generally, electron donating group will direct to C2, C4 position. Okay. But your chlorine is an electron withdrawing group. However, it will direct to C2, C4 instead of C3, C5. So that is just a quick recap. Now, next. Okay. Electrophilic substitution mechanism, all right, just check your answers. Make sure your arrow is pointed, okay? Maybe this is not clear. Okay, I draw the arrow a bit bigger. Oh, sorry, the arrow is the other way around. Here, this side. From the ring to the electrophile, okay? And then you have a semicircle and a positive charge. Make sure you have an arrow to show that the CH bond will flip back in. So the arrow must originate from the bond into the ring. Bond into the ring. Okay? And please remember to show the H plus that is substituted out, because eventually this is a substitution. Somebody goes in, somebody needs to come out. You need to prove that H plus comes out. Now, step 2 is an oxidation reaction. Use bracket O to represent an atom of oxygen from oxidizing agent. So if you were to look at the question paper, all right, the question paper just shows us from here to there. Okay, so all I did was I look left and I look right now. Okay, you need one O on the compound, right? So that's why I need one bracket O. But you remove 2 hydrogen, right? Hydrogen must always come out in water. There is CH3, that means there's 3 hydrogen there. 1 still remain, 2 came out. All right. So hydrogen must come out in water. So you need another oxygen there. So there are total 2 oxygen required. So it's 2 bracket O. Now suggest the reagent for the conversion of K to N in step 3 and step 4. All right. So step 3 is HCN and NaCN. Now they ask for reagent. They never ask for condition. So that's why I put the bracket heat. The condition is heat. This is for 2022 to 2024 syllabus. 2022, 2024, your HCN, NaCN requires heat. Okay. But before 2022, the heat is not needed. Okay. Since this question never asks for condition, then I don't need to write the heat. And step 4 is acidic hydrolysis. Acidic hydrolysis, all hydrolysis require reflux, but because again, they ask for reagent only, hence the heat under reflux is not needed. Okay. Now, acidic hydrolysis, H2SO4, aqueous. You either put the word AQ or you put the word dilute without the AQ, up to you. But you have to provide either one, because hydrolysis means you take the hydro, water. Where is your water? It comes from the word dilute or aqueous. Okay. State the type of reaction that occurs in step 5. Now, for information, step 5 is esterification. But you should know that type of reaction, according to your syllabus, do not have the esterification word. So it has to be condensation. All right. So for those who want to re-look at step 3 and step 4, you may want to rewind the video just now to go and check what is step 3 and step 4. But it's okay. I can quickly go back to the whole route, the whole route, to show you what is step 3 and step 4 again. Now, step 3, as you can see, aldehyde is converted to hydroxynitrile. So you need HCN and NaCN. That is only the reagent. Step 4, you can see your nitrile has been hydrolyzed to carboxylate acid. So you need H2SO4 aqueous. Okay. Now, step 5 is your carboxylate acid to an ester. So this is considered as a condensation reaction. What do you need? Concentrated sulfuric acid. All right. Next. Oh, I have not solved this. Step 7 takes place when P is heated with a weak base such as K2CO3. So they gave us step 7 over here. So what I can see here is that you actually added that whole compound onto the P. And K2CO3 is a weak base. Okay. Suggest why a strong base such as NaOH is not suited for this reaction. Interesting. Oh, let me think. Let's think together. I've forgotten to solve this question. So just give me like a while to think. Ah, I know why. Because if you use a strong base, right, OH, then therefore, the strong base means you have high hydroxide concentration. They will actually undergo nucleophilic substitution. Therefore, hydrolysis will occur. All right. Suggest why a strong base such as NaOH is not used. Because hydrolysis of the Cl will, which Cl? On the CH. Can I put LQ group? LQ, on the LQ. Because there's two Cl, this Cl and that Cl. So the first Cl is a LQ type of Cl, and the second one is an aromatic Cl. So just to be clear to the examiner, I will say that because hydrolysis of the chlorine on the LQ group will occur, okay, will occur instead of the whole two ring seated on it. So if you want the ring to sit on the LQ chlorine, we need to use a base, but we need to use a weak base. If you use a strong base, instead of that whole ring to sit on the Cl, which is the LQCl, your hydroxide from the NaOH will go and substitute on it via hydrolysis. That will be my answer. Okay. Now, Q is optically active. Explain the meaning of optically active. Able to rotate the plane polarized light with an angle in one direction. All right. Optically active means only one direction. Optically inactive means you have one clockwise, one anti-clockwise in opposite direction. Hence, it will cancel off the effect of the angle. Because they say active, so I say in only one direction. It does not really matter whether you chose the clockwise or the anti-clockwise direction of your angle. Okay, so I just state one direction. Give two reasons why it might be desirable to synthesize a single optical isomer of Q for use as a drug. Because if you know that when you have a pair of optical isomer, also known as race-mate mixture, so 50% will be having a medicinal or therapeutic effect for human, and the other 50%, if you're very unlucky, will be detrimental or perhaps maybe no effect. So normally we will only want to produce the best we can. It is desirable to only produce the good 50% and not form both, which is 50% good and 50% bad. All right. So two reasons why. Number one, less harmful effect. Number two, higher efficiency. Okay. That one is a marking scheme from answer from a previous question paper. The previous question paper actually gave 3. All right. So I only put 2 here. Less harmful effect, higher efficiency. Okay. The third one, you can go and find out that particular pass here and find out what's the third answer. Okay. Now, next question. Q is commonly used in conjunction with aspirin. So the pKa of aspirin is 3.49. So this is a weak acid. So basically, you want to remove this proton out. It's a weak acid. So 75 milligram of aspirin dissolved in water to form 100 centimeter cube of aqueous solution. Calculate the pH of this solution. So first, 75 milligram is 0.075 gram. And you dissolve in 100 centimeter cube. I would like to find 1,000 because it's dm cube. 1 dm cube is 1,000 centimeter cube. So 1,000 centimeter cube is 0.75 gram. And I find the number of moles in 0.75 gram, which is 4.17 times 10 to the power negative 3 moles. So this is the moles of aspirin in 1,000 centimeter cube. Okay, now, therefore, the concentration is also the same, called 4.17 times 10 to the power negative 3 mole per dm cube. Now, do you know why I have to find 1,000? It's because otherwise the concentration is going to be mole per 100 centimeter cube. Okay, so we want mole per dm cube. So you find back 1,000 centimeter cube. So therefore, you give me pKa. So pKa, you want to convert to Ka. So Ka is 10 to the power of negative 3.49 equals to x squared, where x squared is H plus and the conjugate base. So you basically x squared is this one. All right, so it's a 1-to-1 ratio. Hence, I just put an x squared over the concentration or the number of the concentration of your aspirin. So concentration is 4.17. So hence I can calculate what is the H plus concentration. So H plus concentration is 1.16. You want to know the pH. So pH is negative log concentration of H plus. Hence my pH is 2.94. 4. So aspirin undergo acidic hydrolysis in the stomach, give the structures of the organic product of this acidic hydrolysis. So you look here, you find your ester bond. So you need to cleave here. So you put the H here and you put back the OH here. All right, so that is acidic hydrolysis. So therefore, this is the answer. Okay. Number 6, amino acids are molecules that contains an amino group and a carboxylic acid functional group. Glycine is the simplest stable amino acid, and the isoelectrical point for glycine is 6.2. Define isoelectrical point. It is the pH where amino acid exists as zwitter ion in its dominant form. This one memorize from marking scheme, previous past year paper. All right. Draw the structure of glycine at 4. Now, if you put glycine under pH 6.2 pH, that means he'll become neutral, zero charge, but must be in zwitter ion form. But pH 4 now is acidic relatively to 6.2. So if acidic means you need to put H plus on your amino acid. So when you put H plus, then your H plus will sit here. So this is the structure of glycine because you have a lone pair electrons on nitrogen to accept H plus. 4 is acidic to 6.2. So you put H plus on your amino acid. Figure 6.1 shows two syntheses starting with glycine. Okay, now let me zoom out a bit. Okay, so you can have a look here. You pause the video to have a look at this whole thing. Now, state the essential condition for reaction 1. Now, if you look at reaction 1, right? Reaction 1, this part here is here. And what you did was you added 2 of, let me change the color. You added 2 of ethyl, 1 ethyl here, another ethyl here. So that means your bromoethane must be excess. All right. Or in other words, your glycine is limited. All right. Limiting factor. Okay. Yep. Now, because if your glycine here is excess, okay, then they will only enable 1 ethyl group to be substituted. Okay, and this part will be H lah. That is provided if your glycine is excess. But now your glycine is not in excess, whereas your halogen alkane is the excess. That's why you have 2 blue pen. Okay, yeah. So over here, state the essential condition. I think this is very interesting. Okay, now if you were to think a bit more simple-minded, right, then perhaps your answer would be ethanolic. But I don't think so simple lah. Because it's only 1 mark. So it's like ethanolic. Yes, ethanolic. I do agree ethanolic is a needed condition. But I would want to target a little bit more on why they have 2 ethyl groups sitting on it. All right, so I continue by writing heat glycine under pressure because normally you all use ammonia. It's called heat ammonia under pressure. So I just change it to heat glycine under pressure. That is a condition. All right, and I add on as a limiting factor. Or the other way, you use excess bromoethane. Okay, I'm pretty sure the answer is inside here, but how do they want to award the 1 mark? Nobody knows. Okay, yeah. If they only awarded to ethanolic, then good for you. Now, number 2, identify the reagent used in reaction 2. Look at reaction 2. Okay, this part here is this part. Okay, so basically you form an amide group. Now, amide can only be formed from acyl chloride and amine. So it must come from benzoyl chloride, or you can draw the structure out here. Okay, please don't use carboxylic acid. Okay, now number 3, draw the structure of the organic product U that forms when your hippuric acid reacts with an excess LiAlH4. If you look at this acid here, LiAlH4, you need to reduce amide. So yes, reduction of amide occurs here. Okay, but did you also realize that carboxylic acid can also be reduced using LiAlH4? So when you reduce carboxylic acid, it will form primary alcohol. And when you reduce your amide, okay, it becomes an amine. So the oxygen here came out as H2O. Okay, so this is my answer. Now next, a molecule of phenylalanine R can react with a molecule of glycine to form 2 dipeptide S and T. So S and T are structural isomers. R and glycine to form S and T. Both are dipeptide. So basically, remember I always ask you all to write amino on the left, acid on the right. Amino on the left, acid on the right. All right. So for those who take biology, the dipeptide name here is called R-glycine, and the T is called a gly-R dipeptide. It's only which one comes first. But you need to make sure that the amino N is on the left and the acid is on the right. Okay, so the S, what I did was I undergo condensation this way with one of the H. So this is the S. Okay, the T version is to take the OH here and the H from this side. All right, to glue. It's just basically swapping the condensation. Okay, yeah? Yep. So that is S and T dipeptide. A student proposed a synthesis of hippuric acid by the reaction of benzamide and chloroethanoic acid. The reaction does not work well because benzamide is a very weak base. Explain why amide are weaker base than amine. Oh, this one, Pascal came up a few times, okay? So the C double bond O in the amide is an electron withdrawing group, and it will delocalize the lone pair electron on nitrogen to form a resonance structure, all right, a delocalization structure. So hence the lone pair on nitrogen is not available to accept proton, okay? Now, Part 2, the pKa of chloroethanoic acid is 2.86 and the pKa for ethanoic acid is 4.76. Explain the difference between the two pKa value. 1 mark definitely got to do with explaining what is a lower pKa value. A lower pKa value indicates it is more acidic. Okay, more acidic. All right, so chloroethanoic acid is more acidic because it has a lower pKa value than ethanoic acid. Why it is more acidic is because the electron withdrawing group, which is the chlorine atom on the chloroethanoic acid, will help weaken the OH bond. Okay, can I add on? You help weaken the OH bond to donate H+. We need to address acid. Okay, and of course, after donating H+, it will stabilizes the chloroethanoic ion. So that's why it is a better acid for chloroethanoic acid. Okay. Donkey. Now, compound V is given here. And they actually label that there are total 5 types of proton in compound V. So this is your V. All right. Now I copy everything. Okay. I copy everything here and I draw it over here. Which one is A, which one is B, C, D, and E. Okay. Now I already written all the answers. You can check. Okay. Now for those, I will zoom out first. That you can see even the chemical shift. All right. Now, OH and NH is always singlet. Okay. So this is OH. This is NH. How come it's orange? I want red. So therefore, here is singlet, singlet. OH and NH is always singlet. It's because they will undergo proton exchange. Okay, theory. So therefore, the signal does not split. So A and E are the OH and NH does not split. Okay, now let's look at the splitting for C. Now this C is a CH2. On the left, there's no proton. On the right, there's 2. So what is the splitting for this carbon over here? Now, your neighbor got 2 proton, all right? So splitting equals to neighbor plus 1. Since your neighbor is 2, which is these 2, okay? So hence, your splitting is 3. We call it triplet. All right? Now, I change color. Let's talk about proton type D, which is this one. All right, type D. Proton type D, on the right, nitrogen, we don't consider nitrogen as neighbors on the right. So that's why on the right is 0. On the left, you got a neighbor that holds 2 proton here. So you got 2 neighbors on the left and you have none on the right. Okay, so same thing, splitting equals to neighbor plus 1. If your neighbor is 2, hence your splitting is 3. So that's why D is also triplet. Okay, now, and then the chemical shift for A is a carboxylic acid type. Okay, I use highlighter. A is a carboxylic acid proton. So you will use 9 to 13 over here. Okay. Now, aromatic here. This is an aromatic proton. So aromatic proton is this part, 6 to 9, HR. Okay. Here, aromatic. Can see, Now then, what is C? C type of proton, right? If you are the CH2, if you look left, you are next to aromatic ring, which is this version. 2.3 to 3. If you look to your right, you're just looking to an alkyl or an alkane. If you look to your right, you would report 0.9 to 1.7, which is the first row. But when you have neighbors left and right, if you look to the left, 2.3 to 3. If you look to the right, 0.9 to 1.7. We always report the higher ppm. So you have to write 2.3 to 3. You cannot write any one of the two. Okay, it is not your choice. All right, you have to always report the higher ppm version. Okay, which is a 2.3 to 3, not the 0.9 to 1.7. Okay, now let's look at the donkey type. If you're the donkey type of proton here, this CH2 here, okay, the highlighter is not working, but it's okay. Here, this one. If you are the CH2 type, if you look to the left, you're looking to an alkane only, so it's 0.9 to 1.7. But if you're looking to the right, you're looking to a nitrogen. If you're looking to a nitrogen, you are an alkyl amine here. So it's 1 point. Oh, sorry, not this, not this. It should be CH2 next to amine. Sorry, let me just change. Here. This one. You are the CH2. When you look to the right, you're looking to a nitrogen, right? So that's the CH2N. You're the green color highlighter, 3.2 to 4 here. Okay. You are a CH2 next to an electronegative atom if you look to the right-hand side. If you look to the left, right, you're looking to a CH2 on the left, which is 0.9 to 1.7. So the rule is to pick the higher ppm. Lastly, you are a alkyl amine, the last case. So the last case just now is this one. You are the NH type of proton, and you are this one, NH type of proton, the alkyl version, 1 to 5, 1 to 5. Okay, so that is the answer. Now, complete the table, okay, by placing a tick to indicate any proton whose peaks are still present in the proton after V is submerged into D2O. Now, D2O will make the OH-NH signal disappear, okay, because of proton exchange. So, OH-NH is this leg and this leg. So, the OH will disappear, the NH will also disappear. So only left the middle three signal remain. So they ask us to place a tick to indicate proton whose peaks are still present. The middle three is still present. That's why I tick B, C, and D. Okay. So therefore, the discussion for the 2024 February March paper is completed. Like I mentioned, this is just my personal answer. It is not Cambridge answer. All right. So if you have any question, you can just leave in the comments below.